Okay, so let's just jump right in. We spend so much time talking about AI alignment and safety, and we're always trying to solve it with, well, with more and more code. But what if we're looking in completely the wrong place? What if the real key to making AI trustworthy isn't in the software at all, but in the physics? Today, we are going to explore a pretty radical idea that does exactly that. It's called geometric actuation.
And this quote right here, this is the whole idea in a nutshell. The universe does not compute, it actuates. Think about it like this. When an ice cube melts in water, it's not running some complex simulation of thermodynamics, right? Nope. Its physical shape, its geometry, interacts directly with the water's geometry, and heat just flows. It's a direct physical consequence. And that principle is the bedrock for everything we're about to talk about. What if AI could be built on that same kind of physical certainty?
But, before we can really appreciate the solution, we have to put a name to the problem. We've all felt it with AI, haven't we? The weird hallucinations, the unreliability, that nagging feeling that it can just sort of drift away from the truth. Well, it turns out that's not just a feeling. It's a real, measurable phenomenon, and it actually has a scientific name.
And that name is alignment decay. Now, the crucial part here, the thing to really lock onto, is that this is a measurable degradation. And AI's grasp on meaning literally starts to unravel over time. And why? Because its knowledge isn't anchored to anything physical. The symbols it's using are totally detached from any kind of concrete reality inside the machine.
And this number shows you just how terrifyingly fast that decay really is. The source calls this a trust half-life. After just 231 logical steps, which for an AI can happen in a tiny fraction of a second, half of the original intended meaning isn't just lost or corrupted, it's physically destroyed, gone.
So, how on earth did we end up in this mess? To understand that, we actually have to go back, way back. We're talking about a fundamental fork in the road for computing, a single critical choice made back in 1945 that basically set us on the path we're on today.
On one side of that fork, you had geometric actuation. Just think of a slide rule or an abacus. The physical position of the bead is the number. The meaning is totally inseparable from the physical object. But that's not the path we took, is it? We took the other path, symbolic computation. That's all modern software. Meaning is completely abstract, just symbols in memory that represent something else. Now, we gained unbelievable flexibility from that choice, but we also cut that essential physical link to reality.
And the result of that choice is what this research calls the detached record. Our entire digital world is built on this idea. A record of a thing is a totally separate entity from the thing itself. I mean, the symbol for water isn't wet, right? And that fundamental separation, that's the origin story of alignment decay.
So, if the problem is that our digital symbols are detached from physics, then the solution is, well, it's beautifully, almost deceptively simple. You have to physically reattach them. You have to ground the fleeting world of software in the unyielding reality of hardware. And this is done with a principle that's captured in one really elegant equation. S equals P equals H. It stands for semantic equals physical equals hierarchical. In plain English, it just means that the system is built so that the meaning of a piece of data is identical to its physical address in the computer's memory.
Let's just boil that down to its absolute core, because this is it. The address is the meaning. There is no separation anymore, none. If a piece of data is about, say, financial fraud, it physically lives at the memory address for financial fraud. The location and the meaning have become the exact same thing.
Okay, so why is this such a big deal? Because when you forge this physical link, you create something that honestly sounds like it's straight out of science fiction, a hardware-based truth sensor that operates at the speed of nanoseconds.
And the absolute genius of this is how it takes a common computer bug and turns it into an infallible feature. Here's how it works. An AI's meaning starts to drift. Okay. But now, because the meaning and the address are fused, that data is now physically in the wrong place, and it has to move. When it moves, it's forced to cross a physical memory boundary. And that's the tripwire. That action triggers a cache miss, a tiny hardware error that now acts as a physical alarm bell, basically screaming that the AI has just drifted from its intended meaning.
And this is where that physical grounding just pays off spectacularly. The old way of trying to correct AI drift is a software loop, and it takes around 300 milliseconds. This new hardware fix, triggered by that physical alarm, 5 nanoseconds. This isn't just a little bit faster, it's an entirely different class of operation.
Let's just put that number up by itself for a second, because it is absolutely staggering. 60 million times faster. That's the difference between software trying to react to a problem long after it's already happened and hardware physically preventing it from ever escalating in the first place. It's the leap from software-based hope to hardware-based certainty.
Okay, so it's absurdly fast. We get it. But what's the so what? Why does this matter outside of a computer lab? Well, because this level of physical certainty isn't just some clever engineering trick. It creates real, measurable economic value.
And to measure that value, we actually need a new term, trust debt. And it's exactly what it sounds like. Just like financial debt, it's a liability that a company builds up in real dollars every single second its AI operates without that physical grounding. Every nanosecond it's allowed to drift away from the truth.
This technology makes that debt totally visible. It sets up 3 crystal-clear operational zones. If the hardware measures that over 90% of the original signal is still intact, you're on the floor. You're good, you're safe. Between 50 and 90%, you're in the drift zone, and that trust debt is racking up fast. And below 50%, you've hit the wall. The system is now provably physically unreliable.
And this brings it all right home to the bottom line. Because you can now physically prove an AI's reliability, you can actually insure it. This analysis shows that a system using this tech can get a net annual advantage of $1.6 million in insurance premiums compared to a standard system. Certainty has a price, and so does uncertainty.
And all of this leads us to the final, and I think very provocative thought. We've just walked through a way to physically measure AI trust with a hardware yardstick. So the question we really have to start asking ourselves is, if we finally have a way to measure this, what happens to all the AI systems out there that have nothing to measure?